So we will, from now on, learn about the some computer vision applications. So far we learned about PyTorch library and also the CNN networks, how to implement that. But now we will learn about how to implement the segmentation, network, and also the pose estimation network. So this is a bit different from the image classification network, which is kind of simple application in computer vision. So we will now, anyways, expand our knowledge towards implementing more complicated computer vision applications. Okay. So this is the slide I showed you in the first class, maybe. So there are lots of computer vision applications, and this segmentation, this is one of the complicated computer vision applications. So in image classification, we assume that there is just one main object inside. And our aim is to classify the images according to their one main object. So this is not that realistic. So the computer vision researchers are extending the method to tackle the images that have multiple objects inside. And there was an object detection approach that detects some useful object with this kind of bounding box representation and then classify the object inside this bounding box. This is the method that can deal with the images having multiple objects inside. And this is more advanced application. So in semantic segmentation, what they do is they detect multiple objects, and at the same time, they classify their labels. So this color is indicating that there is car inside, and also inside the bounding box, they more accurately classify the pixel-wise boundary of the object. So inside this bounding box, there are pixels which is not belonging to the car, right? For example, these pixels are not belonging to car, even though they are inside the same bounding box. So we have to somehow remove and clarify which pixels are belonging to the car object inside this bounding box. So segmentation, for the segmentation, we have to pixel-wisely classify, the object, okay? So that's the segmentation application. And also, this is another important application in the computer vision domain. And this is the called as the application called as the pose estimation. So this is the application for pose estimation for the hand. And this is the application for pose estimation for human bodies. So the aim for this pose estimation application is, to become aware of which poses this hand or these human bodies are having. So for that, what we do is we define some key point. This is called as the key point. There are 21 landmark points are defined for from the hand, and we need to estimate their XY values of these 21 key points. If we know about the locations of these 21 key points, then we can become aware of which poses the hand is having now in the images. So this is the pose estimation problem, and similarly in human bodies, there are 17 or to 20 landmarks are defined in human body like this. there are some points are predefined in human bodies. And then the thing we have to do here for the pose estimation is we have to estimate their 17 to 20 key points, their XY locations. We have to estimate, okay? So that's the pose estimation problem. And nowadays, actually, we are also using this kind of more denser representation, which is called as the mesh, as the pose estimation representation. It has, for the hand, it has 778 key points on it. We have to predefine this amount of point for human hand mesh, and also for human body, we have to predefine 6,000, nearly 6,000 points, the key points on the human bodies. But this is very complicated, so we will learn about this kind of more coarser representation at this lecture. Okay, so anyways, for the pose estimation, what we normally do is we have to predefine some key point, okay, and then we have to estimate their key points locations, XY locations from the images. So that's the pose estimation problem. Okay, so are you guys following this? Okay. So that's the pose estimation and also the semantic segmentation application we will from now on learn about. Okay. So semantic segmentation, as I already told you, we have to label each pixels in the image with a category label. So given this image, we have to label it like this. So this is the sky pixels, and this is the cat pixels, okay, and so on. We have to define their labels like this and have to make this kind of ground truth labels. Okay. And I mean, for developing some networks, the deep learning models for this kind of more complicated application is kind of the research topic a few years ago. So, but I mean, previously, before the deep learning, what computer vision researchers have done for solving this semantic segmentation was like this. So they define small patches. So normally their size is maybe 7 by 7 to 28 by 28 and could be varied. So this is very small window. So normally the full image would be, their size would be this, or even, I mean, if the images are in full HD, then that would be even bigger. So in full HD, normally we have this amount of pixels for width and height. Okay, so this is the pixel size normally we use for the width and height. Okay, and then we make some small patches on the big image, and then we apply some sliding window scheme. Sliding window, it means we will slide this small window in this manner until we meet the last pixels, okay? So this is the sliding window, and by applying this kind of sliding window, we can get diverse patches, okay? So we can extract diverse patches on the images, and then we can apply some CNN network or some of the machine learning algorithms by inputting this patch and outputting some class probability, okay? So this is kind of the extension of the image classification for the semantic segmentation application. Are you guys following this? Okay, this is easy, right? So this network could be classical machine learning algorithms or the CNN architecture, and their role is input some small patches and then classify it to some class. Okay, so this is a kind of naive extension of the image classification towards the semantic segmentation application. But there's one problem in this approach. The problem is that image size would be like this, and we have to apply the sliding window approach using the small patch, and there should be approximately this amount of, if the image size would be this, then there should be this amount of windows. So, I mean, we have to apply this amount, the CNN architectures on this whole amount of windows. Okay, are you agree with that? I mean, if we extract patches and then apply CNN for all each patch, then it means that we have to apply CNN architectures on this amount of small windows. Okay, are you guys agree with that? Okay. But thing is, the classical machine learning algorithms, it is fast because it has shallow layers and there's not much parameter and its speed is relatively faster. But I mean, in CNN, it has deep layers and it normally takes more than 1 second, maybe a few seconds without GPUs. And even with GPUs, some CNN network may take about 1 second. But if we apply one CNN operation this amount of time, then it may take few hours to achieve the semantic segmentation for just one image. Okay, so it is inefficient and impractical. Okay, so if it takes more than hours, if we can get one semantic segmentation result from an image, it is not practical, and maybe it's better to achieve this segmentation map by human hand, maybe, right? So this is impractical. So because of the complexity of the CNN architectures, the computer researchers are becoming to worry about their overall complexity when achieving the semantic segmentation in this way. And the solution might be, there were some other papers that consider how to extend the CNN architecture towards the semantic segmentation, but the solution, there have been very, elegant solution to solve this problem. Okay, so that's actually this shown in this slide, and this is showing the encoder. We normally call this architecture as the encoder decoder architecture. So we normally call this the earlier part, the earlier layers as the encoder, and the later layers as the decoder. Okay, so that's why we call this architecture as the encoder-decoder network. And I mean, encoder part is similar to previous image classification networks, the feature extractor layers. So these, they are constituted with the convolutional layers and also the pooling layers and also the ReLU activation layers. Okay, so this is the normal operations, which is, the main blocks for the CNN architectures. Okay, so they tend to decrease the size of the original input images. Okay, so when you set the stride more than one in convolutional operation, the image size would be become less than the previous input. And also if you apply pooling, then also the output size would be less than the input size, okay? So this encoder, because they are composed of the convolution operation, they tend to decrease the size of the input images, okay? I agree with that, okay? But I mean, we have to have some differentiable layers. We have to have some differentiable layers that can upsample the size of the images, the size of the intermediate responses. I mean, we have to upsample their dimensions, okay? And at the same time, if that operation can be differentiable, then we can stack that layers and can make this kind of decoder network. And then if we are given input and the ground truth, the segmentation ground truth, maybe we can just train this network to infer this type of the segmentation output, okay? I mean, if there could be this kind of operation that can upsample the responses and at the same time differentiable, if there is operations like that, we can use it to make our deep network, and then we can train that network to output the segmentation maps, okay? So without applying CNN architectures this amount of time, we can achieve this by one pass of the input image, okay? So are you following this? 이해가 되나요? So, and computer vision researchers are searching for which might be the operation that could be located here, okay? So they search for the operation that can upsample the previous layer's input and at the same time differentiable, and found that that operation could be this transposed convolution operation, okay? So this is the convolution operation we already learned. So what convolution operation does is, let's say this blue is the image pixels, okay? This is the input image, and this is the output. Okay? And this green, gray, this 3 by 3 gray window, which is moving, is the filter corner. Okay. And you can know that when locating filter corners here and element-wisely multiply their filter coefficients and image pixel values, and by adding them, you can calculate the forced output map, okay? And then by shifting this window by 1 pixels, and you can locate the filter corners here, and by applying the element-wise multiplication between coefficients and the input pixels, and by adding them, you can find the second output pixel, okay? And you can do this by shifting filter corners in this manner and finding the output pixels in this manner, okay? So this is the convolution operation we have already learned, okay? And what transpose convolution, before that, important thing here is, this convolution is composed of the multiplication and addition operation. So this is the differentiable operation, okay? It means the output could be differentiated respect to their input and respect to their parameters, which is the corner coefficients, okay? And transpose convolution operation, what they do is similar to the convolution operation, okay? Here, gray is 3 by 3 gray window is also denoting the filter corners again. And this is the output map. And this blue is denoting the input again. Okay. Their operation is actually same as before. So when the corner is here, what they do is same as before. Multiplication between coefficients of the filter corner and the image pixels. And by adding that, they calculate the first output map, and then they shift the window by 1 pixels and get the next output pixels, yeah, and so on. So they does this in the same manner as input, same manner as the original convolution operation to calculate the output pixels. Okay, so they are also composed of both multiplication and addition operation. So I mean, they could be samely as the convolution operation is differentiable with respect to their filter coefficient and also respect to their input values. Okay, so that's differentiable operation, but you can notice that the input size here is 5 by 5, and here the output size would be 5 by 5. So convolution operation, they normally keep the size of the input, or they tend to lessen the dimension of the input. But here you can notice that their input size 4 by 4. Actually, this transposed convolution, they can upsample the input signal, their dimensions, okay? So this is the operation that can meet two conditions we are required in this decoder, okay? They can upsample the input signal, at the same time they are differentiable, okay? And I will show you more details about the transposed convolution. And actually, you can see their operation is already implemented in the PyTorch. Okay, so previously the convolution operation, their function which is defined in PyTorch was nm.comp2d, but here you can see their operation is comp transpose 2d. Okay, and the thing you have to specify is the input channel size and output channel size, samely as the convolution. And you also have to define the corner size and stride size. Okay, so you can easily use this transposed convolution transposed convolution layers, which is defined in the PyTorch. Okay, and I will show you the case of the transposed convolution with zero padding and stride 1, and when using the 2 by 2 corner. Okay, so here we have input size 5 by 5, and we have the 2 by 2 corner here, and we will use the stride 1. Okay. By default, in transposed convolution, we first apply the zero padding around the images. This is the original input image, and by default, we apply 1 zero padding in normal transposed convolution operation. So now the input size becomes 6 by 6, and then you will apply the normal operation, which is same as the convolution operation, to calculate the output pixels. Okay, so when a corner is here, then you will apply the element-wise multiplication between the corner coefficients and the image pixels on it. And by adding them, you can calculate the first output, and you can shift the windows by the stride. Okay, so this is actually same as the convolution operation, but the thing is, because by default one zero padding is applied, the output size becomes to be bigger than the input size by default. Okay, so now the input size was the 5 by 5, but the output size becomes 6 by 6. Okay, and here also interesting things happen if you change the stride. So previous slide, it depicts the situation where the stride was 1, but here the stride is 2 now, okay? And in convolutions, if you change the stride, the output size becomes smaller, okay? So in convolutions, the stride means how much you will shift the windows, okay? And if the stride becomes larger than 1, the output size becomes lessened, their dimension becomes lessened, yeah, in convolution operation, but in transpose convolution, the opposite happens. So let's say your input is 3 by 3, but if you set the stride as 2, here what happens is your input pixels are located with one offset. Okay, so your input is located with, with these 2 offsets. Okay, so your input size is actually become larger than before if you set the stride. If you set stride larger than 1. Okay, and then if you apply the convolution operation, standard convolution operation, and after that you will apply the 1 zero padding, which is the default setting, and then you will apply the standard convolution operation on this enlarged input image. Then you can get the large output output map. Okay, so this again leads us to have a larger output map compared to the input map. Okay, and also the opposite thing here in transpose convolution is, if you said previously we explained about the zero zero padding situation, but here I will explain about the 1 zero padding situation. When you set zero padding larger than 0, it means it can enlarge the output size in convolutional operation, but here in transpose convolution, the opposite happens. So I will show you why it's like that. So this is the input image whose size is 3 by 3, and this is the corner whose size is 2 by 2. So because the stride is 2, we will samely constitute the input images same as here, right? But the thing is, because we are using zero padding 1, we are actually removing zero paddings once. Okay, so actually, if you set zero padding here larger than 0, it actually effect to reduce the boundaries, the padding numbers. Okay, so because it is set as 1, we will remove the boundaries once. But if you set this as 2, then it will remove the boundaries twice. Okay, so this would be your input image if you set the padding as 2. Okay, so zero padding, it has also the opposite meaning in transpose convolution compared to the convolution. And then if you apply the convolution operation on here, then this would be your output size. Okay, so in convolution operation, if you set zero padding larger than 0, then it means it leads us to have the larger output. But here, if we set zero padding larger than 1, larger than 0, then it actually reduces the size of the output for us. Okay, so this is the transpose convolution operation, and actually this is the phenomenon. I mean, transpose convolution is. I will show you why they are called as the transposed convolution in the subsequent slide. But actually, they tend to have the opposite operation to the original convolution, and I will show you why it happens. So this is the original convolution operation, and this is the filter corner whose size is 3 by 3. And to obtain the output, what you do will be like this: applying filter corner on here and doing element-wise multiplication. And by doing addition, you can get the first pixels in output map. And then you can shift this filter corner by 1 pixel and do the same to get this output pixel. And by shifting the filter corner here and doing the same, you can get the third pixels in the output map. And also you can do same for this last pixel in the output map. This is the convolution operation. Okay? But the thing is, the convolution operation can be implemented in the matrix multiplication. So when you implement this convolution operation in the code level, what you will do is not this kind of sequential algorithm can be easily understandable, but it's not very efficient for actual implementation. So, if you understand the convolution operation as the matrix multiplication, it is easier to implement in the computer and also easier to parallelize each operation. So we normally implement the convolutions as the matrix multiplication. So this is the input which have seen here. Okay, this is the input, but the convolutional kernel, this is a bit manipulated like this, and actually their weights are somehow re-engineered to be here. Okay, and they are somehow shifted to make rearrange it like this to constitute the convolutional matrix. So actually, when you implement the convolution operation in the computer, in the code level, actually, the convolution kernel, they are implemented as the convolutional matrix using some rules. And the thing happens is you will multiply this convolutional kernel matrix with the input images. But the thing before that, you have to transform the input images, which is in size 4 by 4, into 16 by 1 dimensional vector first. And then this is the transformed input, which is the 16 by 1 dimensional vector. And this is the convolutional matrix, okay? And then the thing happened here is matrix multiplication. And then you can get 4 by 1 output vector. And if you rearrange this 4 by 1 vector to 2 by 2 square signal, if you rearrange this to 2 by 2 signal, then this is sanely obtained. Okay, so this is the thing we understand as the convolutional operation, but the thing actually happens inside the code is this kind of matrix multiplication and rearranging the vectors into the square matrix. Okay. This is the convolution operation, okay? But the thing is, the transpose convolution actually does is this. So previously, the convolutional matrix, they are in this form. But if you apply the transpose operation in linear algebra, transpose means changing the width and height values. So if you transpose one matrix, one array, then it will have this type of matrix. So are you guys aware of this? Do you know the transpose operation already? Okay. So if you transpose one matrix, then it leads to this type of the array whose width and height values are interchanged. Okay. So why transpose convolution operation is called as transpose convolution is their filter convolutional matrix are transposed. They are actually transposed from the original convolution operations convolution matrix. And then it is multiplied with the input image. There are, flattened vector. And then you can get the output vector, which is actually larger than the input vector. Okay. So you have to notice that their input values, their dimensions are less than the output dimension, but in the original convolutions, their input size is larger than the output size. Okay. So the thing which makes the characteristics I already explained here is this kind of things. Okay, if you transpose the original convolution matrix, then the previous attributes are, obtained. Okay, but the thing actually happens is we transpose the convolutional matrix to make this transposed convolutional matrix, and then apply the matrix multiplication on the flattened input. And then if you rearrange this vector to the squared image map, then the final output would be obtained. Okay. So indeed, you can notice that this transpose convolution matrix operation is differentiable because their core operation is composed of the addition and multiplication, same as the standard convolution. And at the same time, they are expanding the input signal to the larger output. Okay, they are actually upsampling the input signals. Okay, so they can be used in the subsequent layers in the semantic segmentation network. Okay, and then if we train the both convolution layers and transpose convolutional layers to make it output this kind of segmentation output, then at the testing, we can get some segmentation map from the arbitrary input images. Okay. Actually, this would be the second assignment. So maybe you have to implement this kind of semantic segmentation network given some data. Okay. But maybe you can use this kind of encoder-decoder network. Okay, so as we learned, this is defining some encoder-decoder network, and we have to define two types of intermediate layers. The first is the encoder layers, and the second is the decoder layers. And encoder layers, you can see that they are composed of the sequence of the convolution operation and the activation layers. And decoder, we define it using the transposed convolution operation, okay, and also using the activation layers. During the forward pass, what you have to do is inputting the original image and apply encoder first and decoder later. and get the final output, which is the same, which have the same dimension as the input image. Okay. So maybe in the assignment, you can use this kind of encoder-decoder network, and by supplying this kind of segmentation data to train this network to output this kind of segmentation prediction. Okay. So the optimizer and the training code might be same as before. Okay. Are you guys following this? Okay. And yeah, this is the example for training the encoder-decoder network. Actually, your model is here, defined here, okay? And you can apply this kind of training code to train the network, okay? And samely as before, samely as the image classification network, you can use cross entropy loss. So even though your final output, so this is the encoder-decoder network, and this is your input image, and this is your output segmentation map. Even though they are in the 2D space, you can apply cross entropy rules, same as in the image classification application. Your ground truth would be also in the 2D map, having some digitized. Maybe if you have n classes, this value would be 1 to n or 0 to n minus 1. And maybe the ground truth would be also have this discretized integer arrays. And you have to estimate some probability map, okay, here, okay, and it have to coincide with this ground truth vectors, okay, using that can be trained by this cross entropy loss, okay. And I will explain this part a bit later, image generation part a bit later. And the next thing we have to learn is the pose estimation things. So in pose estimation, I already explained to you, we have to define some key point on the human bodies, okay? So this point would be from maybe head top, and this point would indicate the neck, and this point would indicate the right hand, and this point would be left hand. Somehow we define anyway some key part from the human bodies. We can define maybe 14, or we can expand it to 20, okay? Anyways, we have to predefine some key point from the human bodies. And we also have to, for collecting the training data, we have to annotate their XY positions, okay? We first have to define the key point, and for collecting the training data, we have to collect their 14 key points XY coordinate. And here what we do for training the network for the pose estimation application is we train this kind of CNN architectures to output 14 key point XY joint. So there could be 28 dimensional floating values that explains about the XY coordinates of the 14 key point, okay? So there could be a lot of loss functions for achieving this, but normally what we do is, anyways, this network will output 21 floating values that describing the XY coordinate of the 14 key point, and we can apply the L2 loss between this output and our ground truth, okay? For the training data, we have to collect this, the ground truth values for this 28 key point. okay, their coordinate values, and then apply this kind of L2 loss, which is the mean square error loss or Euclidean distance between ground truth and the prediction values, okay? So using these loads, we have to train this network so that it can predict this 21 key point from the unseen testing data, okay? That's the post-estimation network. So are you following this? Okay. Not that different from the image classification application. So we can train this network using the same code, which is the loss dot backward and optimizer step, okay? The different thing is our output of the CNN network is now 28 rather than the number of class probability vector. And we may have to use different loss function, okay? And this is another, this is famous paper whose name is Convolutional Pose Machine. And this is published in the paper, CVPR 16 paper. They proposed this kind of architecture. So previously, when achieving the pose estimation application, we directly regress the XY coordinate from the image. We directly map it to 28 vector, dimensional floating vector, which describes this XY coordinate inside. But what this paper says is, we can, rather than directly regressing the XY coordinate their values, we can instead estimate this kind of heat map representation. And for the network, in between this image and 21 coordinate, in previous way, there are CNN, and CNN had to map these image pixels, image arrays into these 28 dimensional floating values that describes the XY coordinate of the key point. But what the authors are proposing is, from the input images, their arrays, they can map it to 14 dimensional heat maps that, and each this 2D array is describing where each key point are located. So these kind of things are heat maps, and they may have all zero activation and have the activation like this only for the regions where the joints are located. So they may get this kind of 14 heat maps, okay? So this is the heat map for right hand, maybe. And this is the heat map for left hand, okay? So for each 14 key point, they may define heat maps. So here there are 14 heat maps, actually. Okay, so mapping, train the CNNs to map input images towards the direct coordinate values. Rather than that, this paper, they are saying that transforming the images into this kind of same images that describes this kind of heat maps is rather easy. So actually, in post-estimation, this heat map representation is frequently used as the proper output rather than the coordinate values nowadays. So, so that's why here this kind of outputs are described. Okay, and also this would be on maybe in assignment 2. There are two tasks. The first is the semantic segmentation, and the second is the pose estimation. And you can actually see what exactly is this post estimation heat maps, okay, inside the assignment. Okay, so actually both application, the post estimation and semantic segmentation, those are materials for our assignment too. Okay, and you may also use this kind of models. This is actually the CPM 2D pose. CPM means convolutional pose machine. And this is the architecture for 2D pose estimation. And what they do here is, this is the same class we defined for our architectures as before. So this is the same method. And they first define the constructor and define several convolutional layers here. And in forward function, they define several forward functions. And from the input image, what they do is they apply convolutional operation and activation several times and doing the max pooling. And anyways, apply a lot of convolution operation. And then they encode the features in the middle. And they from the feature, they estimate the first heat map. This is the first heat map. And also by concatenating the first heat map and the feature, this is the feature, intermediate feature, and then apply another stream of the convolution operation and estimate the second heat map. And then again, concatenating the feature obtained here and also the second heat map obtained here, they apply another stream of the convolutions to get the final heat map. And in their paper, they originally trained the heat maps by applying L2 losses between ground truths, and this activate three times estimated heat maps. So they apply actually 3 L2 loss between ground truths and these 3 heat maps to train the entire network here. Okay. So I mean, if we can get the ground truth as the heat map format, and if the output is also heat map, we can apply L2 loss to close these 2 arrays. Okay. So this is denoting the first heat map, second heat map, third heat map, and this is the input. And we apply first the streams of the convolutions to get the first heat map, and the L2 loss is applied here once, and then apply several stream of convolution to get the second heat map again. And also we apply several convolution operation to get the final heat map here. And we actually apply L2 losses for these 3 heat maps. Okay, so that's how these CPM networks are trained. Actually, we will provide the CPM, the same code as before, as this slide for the assignment too. And the thing you have to do is train this network, I mean, for given training data, okay? So using this method, anyways, you can achieve the post estimation things. Okay. Okay. And maybe later, I mean, next class, we will also learn about the image generation part, which is not very difficult, but I will resume next class from here. Okay. And next class, we will also learn about, start to learn about the object detection application, which is actually the very important part of the computer vision algorithms. Okay, okay, let's finish here for today's lecture. Thanks, and see you in next Wednesday. Okay. 네, 그 키포인트의 위치, 이미지 상에서 위치. 그래서 실제 위치는 네. 히트맵. 네. 히트맵은 이제 이게 디멘전이 이미지잖아요. 히트맵은 그 위드스 하이트의 어떤 어레이가 있고, 그 어레이 안에서 뭔가 뭐 액티베이션이 되냐 안 되냐 그거를 이제 학습을 하겠죠. 네. 그러니까 이미지랑 같은 디멘전이거나 아니면 조금 더 다운 샘플링된 형태일 거고, 네. 이게 뭐 이미지가 256 바이 256이면 얘가 32 바이 32 맵이에요. 네. 그게 조인트 개수만큼. 네. 출석인가요?
과제 관련 질문인데 그 테스트 셋을 이제 채점하시는 분이 가지고 있는 테스트 데이터를 사용하시는데 저는 이제 데이터 학습할 때랑 이제 제 걸로 이제 테스트를 할 때는 이름에다가 이제 true 값을 넣어가지고 그 로드를 하면 그 true 값을 거기 이름에서 빼내고 그다음에 그게 이제 정확하게 맞는지 체킹을 했는데 그러면은 그 테스트 데이터 형식이 사람마다 다 다를 것 같은데 저는 이제 뭐 이미지 데이터 뭐 1분
파일 이름
네, 파일 이름 그런 식으로
파일 이름은 사실 필요는 없는 것 같아요. 그러니까 인퍼런스 코드를 어쨌든 저희한테 주시고 그 모델 웨이트도 주시고 하시잖아요. 제출하시잖아요. 그러면 저희가 알아서 테스트를 해볼 거거든요. 사실.
그래요? 그냥 거기 파일 이름으로 해서 그냥 알아서 거기 잘 써놓으면 채점을 해주시는.
그렇죠. 그거는 저희가 할 수 있을 것 같아요.
그다음에 과제 제출 그게 한 1회로 제한돼 있어가지고 혹시 늘려주시면.
1회로 제한돼 있나요? 제가 한번 늘리겠어요. 확인해서. 네.
일단 수업에서 히트맵 구한 거를 MSE 로스를 써서 GT랑 이제 학습을 한다고 했는데 그러면 GT 히트맵이 따로 있는 건가요?
그렇죠. 그거 만들어야죠.
그럼 마스킹에서 1110000만 해서 약간
그런 식으로 그렇죠.
막 핸드 부분에 이런 식으로
그렇게 돼 있어요.
이런 식으로 하는 거예요. 그리고 저도 아까 저 친구랑 똑같이 이미지의 네임이 1시간 58분 미닛에 이렇게 id.jpg를 해놔서 이게 이런 식으로 쭉 있거든요. 그래서 이게 이미지를 받으면은 그 이미지에서 시간하고 분을 파싱을 하고 뒤에는 아이디는 그냥 버리거든요. 이게 이렇게 하는 이유가 데이터 양을 늘렸을 때 이제 그 같은 시간이어도 다른 색깔이면 다른 데이터니까 이제 듀플리케이션을 막으려고 아이디를 넣었거든요. 그래서 근데 이런 것도 전부 다 그냥 리포트에 적어두면
그렇죠.
테스트에서 그냥 감안을 하면서
그렇죠. 테스팅 코드가 근데 이거랑 영향은 없잖아요, 사실.
이제 테스트를 할 때에도 데이터 로드를 할 때
저희는 하나하나 샘플을 그냥 있는 거를 불러서 테스팅을 하거나 큰 영향은 없을 것 같네요.
그러면은 저희가 테스트 코드를 이제 4번에서 프로블럼 4번에서 짤 텐데 이거를 기반으로 테스트 코드를 학생들마다 다르게 그냥 적용을 하시는 건지.
네, 그렇죠.
그럼 저희가 쓴 이 4번 코드를 기반으로 이제
거기서 어쨌든 웨이트 불러서 파일 이름은 크게 상관없잖아요. 그러니까 그거는 정답이랑 비교를 해서 정확도를 매기기 위한 거고 어쨌든 아웃풋은 나오지 않아요.
그렇군요. 그러면은 그냥 포워드에 X만 제대로 들어가면
그렇죠. 그러면은 그 테스팅 코드에서 어쨌든 아웃풋이 나오면 우리가 눈으로 비교할 거고. 그럼 상관은 없잖아요.
그러면은 제가 트레인이랑 인퍼런스 하는 거랑 함수를 다르게 짜는데 그것도 그냥 거기서
그건 상관없어. 원래 그렇게 해야 될 것 같은데.
이게 약간 트레인 할 때는 노멀라이즈 값이 나오고 인퍼런스 할 때는
그거는 이제 정수값이 나오게끔 그건 처리를 해주셔야죠.
그거는 저희가 해가지고 4번에서 했던 거랑 비슷하게 테스팅한다고.
네네네.
I don't know if I am allowed to ask this question because it's regarding the assignment, but I am having problems with choosing how I want to express the data in my model. For now, I have chosen to predict the cosine and sine of the angles for the hour and minute angles. So basically, I have a CNN that outputs 4 values. I am only using one loss, which is the MSE loss on the vector of 4 elements,
Mm.
but it's really not working. So I don't know.
Maybe I'm encouraging you to change the root functions then
Okay.
and supply more data. So how many images are you using as the training data?
I am using about 200 images per
200.
per time
Maybe you have to use more than 10,000
per
images
class and per time.
per over maybe over.
Okay.
Yeah. So I mean, are you using few hundred images for one time?
Yes. For example, for a clock that indicates 1 hour and 30 minutes, I have 200 images.
For that.
Yes.
So and
of
how
several
many
colors.
configurations? How many data you have for entire? I mean, how?
About 144,000.
144,000. It's not that small then.
But yeah, I don't know why it's especially the tests.
Yeah, but I mean, normally we don't use the cosine and sine.
Oh, okay.
Yeah, I mean, you can normalize it to maybe 0 to 1.
Okay.
You can maybe you can normalize the angles to 0 to 1, and maybe enforce your output, network output, to estimate 0 to 1 by applying some sigmoid.
Mm.
Yeah, and then compare with the, you have to I mean, normalize the ground truth case to 0 to 1 and compare it directly without applying cosine and sine.
Yes, I tried with the angles, just predicting the angles in radians, for example. But the problem is 0 radian and 2 pi radians are supposed to be on the same place, but with the loss, they're very far apart.
Yeah, but I mean, if you set it as 0 to 2 pi and normalize it to be 0 to 1, I don't think that's problems maybe.
Okay, because I was scared that
yeah, I mean, that's one specific case, right? So you don't have to worry too much about that.
Okay.
Yeah.
Okay. That was why I took the cosine and sine, because you didn't have this problem. Okay, well, I will try going back to angles.
Okay.
Thank you.
Yeah. 질문 있나요?
기본적인 건데 제가 들어가지고 이제 아까 인코더 디코더 할때 인베딩을 하잖아요. 그리고 오늘 다뤘던 주제가 디코더 쪽에서 트랜스포스 컨버전 하고 그랬는데, 그러니까 컨버전 해서 줄이는 거는 인코드 인베딩 하거나 클래시피케이션 할 때는 그냥 당연히 이제 컨버전이 있어서 특정 지역에서 피처가 익스트루션 되고, 그게 점점 가면서 이제 그러니까 계산량을 줄이면서 뭐 정보도 살리고 이런 식으로 한 다음에 뭐 일단 플래튼으로 가정을 하면은 이제 뭐 엑리스트 예시로 들면은 당연히 이제 플래튼 됐을 때 인베딩 되는 것처럼 뭐 10개로 치면 그냥 소프트엑스까지 치면은 0번째 레이어의 값이 좀 크고 그렇게 되잖아요. 근데 그러니까 이렇게 생각해보면 하다가 컨버전을 인코더를 할 때 했을 때 그냥 이렇게, 그러니까 1번째 정보에 뭐 강아지가 있다. 강아지 얼굴 정보가 보통 1번 셀, 그러니까 픽처의 첫 번째의 값이 높고 그런 식으로 인베딩이 되는 게 아닌가라고 생각을 했고, 그냥 이거 아래에 있는 거는 그냥 랭귀지 같은 거 할 때도 저희 예시로 이제 킹이랑 퀸 이런 걸 많이 쓰잖아요. 그 비주얼라이제이션 하면은 이제 남자인 맨인 부분이 이제 3번이 많이 있어요. 여기가 좀 값이 높고 이제 뭐 빼서 비교하는 것도 그렇게 하잖아요. 그래서 이제 인베딩을 이렇게 하는 것 같다라는 거가 일단 맞은, 그러니까 그
인베딩이라는 게 뭐죠? 중간 피처?
네네, 여기 인코더 디코더 사이
중간 피처에는 따로 근데 슈퍼비전 같은 거는 안 보는데 여기는 인코더 디코더는.
그렇죠?
네. 근데 여기가 우리가 인코딩을 어떻게 한다를 만드는 건 아니거든요.
그러니까 인베딩이 그러면은 그러니까 그 이런 식으로 특정 부분이 있으면, 공통된 부분이 있으면 데이터셋이 여러 개일 거 아니야. 그래서 공통된 부분이 있으면은 결국 인베딩 벡터에서는
특정 번째에 특정한 뭐 특징을 나타내는
뭐 그렇게 될 수도
이렇게
있겠죠.
될 수도 있다고 봤는데
네.
이런 식으로 봤을 때
음.
이제 여기까지는 이제 이해가 됐는데
음.
디코더를 할 때 뭐
음.
옵샘플링을 하든 이렇게 하든 하잖아요. 뭐 이렇게 나눠서 배치하기도 하고. 근데 그게 조금 이해 안 됐어요. 그러니까 이거 왜 이게 작동하는가? 그러니까 다시 작동하는 거는 증명이 됐잖아요. 근데 왜 잘 작동하는지가 잘 이해가 안 돼가지고.
아니, 근데 사실은 뭐냐면 그 얘기는 그냥 이거 인풋에 대해서 우리가 세그멘테이션을 하고 싶으니까 이런 데이터를 많이 모으잖아요.
네네.
근데 사실은 딥러닝 뭐 어떤 아키텍처가 와도 되는데
네.
이제 어떤 아키텍처가 와도 파라미터 업데이트 계속하면은
네,
이 데이터에 더 잘 동작하게 되는 거잖아요. 근데 여기서 하고 싶은 거는 업샘플링을 하고 싶은 거예요. 왜냐면
그냥-
컨볼루션을 쓰면은 계속 줄기만
줄어들고.
하니까.
네.
근데 어떻게 보면 자기 자신 크기만큼 뭐 업샘플을 하는 거를 하고 싶은 건데
네.
그러면 이런 질문은 사실 나올 수 있어요. 왜 이걸 줄여야 되냐?
네.
줄였다가 펼치냐?
네.
그거는
반대로.
줄이면 임베딩이 이 전체 이미지에 대한 뭔가 정보를 그래도 좀 인코딩 했다가 다시 펼치는 느낌이라서
네.
조금 더 잘 쓸 수 있죠. 그래서
그러면은
이제 보통 줄였다가 펼치긴 해요. 네.
반대로 늘렸다 줄이는 거는
늘렸다 줄이는 거는 처음에 이제 근데 생각을 해보면 사람들이 늘리는 거를 원래 좀 될까? 막 이런 생각을 좀 했었거든요. 그러니까 원래 그냥 필터 업샘플링만 하는 거가 원래 안 되잖아요.
그렇죠.
그 이미지 업샘플 해봤는지 모르지만 업샘플하면 중간에 다 뻥뻥 비잖아요. 그러니까 그게 되게 안 되는 오퍼레이션인가는 걸 이미 알고 있어서 업샘플하는 거에 좀 거부감이 있었어요 원래. 근데 이제 이런 업샘플 만들고 얘를 학습을 하면 중간을 학습 기반으로 메워줄 수 있구나를 이제 어떻게 보면 요 트랜스포즈 컨볼루션 할 수 있구나 이제 알게 된 거죠.
결국에 뒷부분에 하는 거는
네.
그 웨이트 옵티마이제이션을 잘 해서
네네 그렇죠.
잘 채우는
네, 잘
역할
채우려고 하는 거죠. 네.
존재하는 거 앞에 거는
앞에 거는 뭐 어떻게 보면 피처 익스트랙터 역할을 하는 거고.
그 피처 익스트랙터에만 봤을 때 이제 완전히 리버스 되는 형식이 아니라 그냥 얘는 얘 따로 옵티마이제이션인 거죠.
아니지. 이거는 어떤 슈퍼비전이 걸리지 않고요. 슈퍼비전은 얘만 걸고 이 중간 네트워크는 사실 뭐가 돼도 상관이 없는데 그나마 이제
결국
좀 뽑고 펼치는 방식이 잘 되더라. 그래서 이렇게 좀 쓰려면 한 건데 요거를 생각한 이유는 기존 이미지 클래시피케이션 네트워크가 이미 이미지 피처 익스트랙션을 좀 하잖아요.
네.
어떤 이미지에 대한 정보를 함축된 어떤 레이턴트 벡터로 만드는 것까지 해놨으니까 그거를 어떻게 다시 디멘전을 펼칠까 뭐 이런 고민을 좀 한 거죠.
전체가 이제 옵티마이제이션.
네, 그렇죠. 네.
11월 6일 날 이거
발표?
이게 3시 15분까지 가야 돼서
그거 얘기해요 저한테. 메일로 주세요.
네.
메일로 해서 증빙 같은 거 이거 해서 뭐 좀 주면은 될 것 같은데.
이날 수업은
알겠어.